Hi, welcome to the 15th lecture, the third flipped lecture. Today we're going to be talking about free energy and intermolecular forces. All right, last time on Thursday we talked about the third law of thermodynamics, that is entropy of a perfect crystal at absolute zero is zero. And from this third law we got this concept for absolute energy. Unlike enthalpy, entropy actually can have absolute values, not just a change in entropy like we measure for enthalpy. And we talked a little bit about how to calculate entropy from the molar entropy values that you can find in tables. Today we're going to talk about when a reaction is spontaneous. Again, we're going to reprise this question. And we get this term free energy, G, and this describes spontaneity of a reaction. And we're going to talk about the relationship of G, free energy, to enthalpy, entropy, and to temperature. And we're going to talk again about this thermodynamics in relation to biology. So we're going to get into a little bit of biology towards the end of this lecture, and then we're going to talk about intermolecular forces, and we're really going to focus on the aspects of biological significance when it comes to intermolecular forces. So let's start off with a couple review questions from last time. So the first question, which statement about standard molar entropy is correct? Take a few minutes, pause the presentation, and see if you can answer this question. Okay. So what do you think is the correct answer? Well, let's go through these. Part A, entropy for bromine gas is less than the standard molar entropy for a bromine liquid. Well, this is incorrect. If you remember from last time, gases have more entropy than liquids, so A is incorrect. B, the entropy for pure oxygen is greater than the entropy for oxygen dissolved in water. And this is true. So this is the true statement. If you remember from last time, a pure gas, a gas in a gas phase, has a higher entropy than gas that is dissolved in water. And let's look at C and D anyways, even though we know B is the correct answer. So entropy for potassium chloride solid is greater than entropy for potassium chloride dissolved in water, an aqueous solution, and that is incorrect. Entropy is greater when a solid is dissolved. And D, entropy of N2O4 gas is less than entropy for NO2 gas, and that is also incorrect. If you remember, more complex molecules, as long as they're in the same phase, have higher entropy. All right, let's try a second question. In a spontaneous process, there's an increase in the entropy of the universe. We know that from the last couple lectures. So if we define this term delta G as minus T times delta S of the universe, what is the sign of delta G for a spontaneous process? And this is going to become important. So delta G is the free energy, the change in free energy. Entropy has to be a positive value for a spontaneous process. But if we're multiplying that by minus temperature, delta G then has to be a negative value for a spontaneous process. So delta G, the free energy, and entropy are inversely related. For a spontaneous process, entropy has to be positive, entropy of the universe has to be positive, but delta G has to be negative. All right. Let's get started with some material from chapter 20.3, free energy. So if we have an example here, if you have a cat, pick up a cat and drop it, it always lands on its feet. A piece of bread with butter on it, if you drop that, it always lands butter side down. So what happens then if you strapped a piece of bread with butter on it to a cat's back and picked it up and dropped it? Well, it wouldn't know what side to land on, so it'd just sit there and keep rotating. If you attach this to a generator, then you can generate infinite amount of energy. Well, this is not what we're talking about when we talk about free energy. What free energy is the energy available to do useful work in a process. And what we're going to be talking about most of the time is a free energy change, so delta G, change in free energy. And this is the change in free energy of a process occurring at a constant temperature and pressure. For the most part in this class, we're going to be talking about constant temperatures and constant pressures. And as we've saw before in the second question, for a spontaneous process, delta G has to be a negative value. Delta G, this free energy, it's called, the sign is a G because it's known as Gibbs free energy, and it was introduced by Josiah Willard Gibbs in 1875, and that it might seem kind of funny that we use a G, but it's actually because it's known as Gibbs free energy for its creator. So free energy, again, it's the energy available to do useful work. If we write our equation for the change of internal energy in a system, we have Q, which is heat, plus W, work. Some of the energy is always going to be lost to heat the surroundings. That's a Q term. Some energy is also going to be lost due to entropy. And this again is a factor that involves Q. So the amount of energy that's left to do work is less than the total energy. And there's a term for this we can use, efficiency. And efficiency is the work done divided by the energy consumed. So the work done divided by the total energy that would be available. Let's look at delta G and how it is actually derived. So we know from the second law, a spontaneous process, S, the entropy of the universe, has to be greater than 0. And the entropy of the universe you can write as the sum, entropy of the system plus entropy of the surroundings. Now if we look at the change of entropy of a system, we can write that as delta S system. The change of entropy in the surroundings, if we remember from last time, is equal to minus delta H of the system, so minus the heat of reaction, divided by the temperature at which that reaction occurs. And we can plug these values in to our equation from the second law. This becomes delta S of the universe equals delta S of the system minus delta H of the system divided by temperature. And this has to be greater than 0. If we multiply the equation through by temperature on both sides, what we get is minus T times delta S of the universe. So we're multiplying through by minus temperature, is going to equal delta H of the system minus T times delta S of the system. So this is a way that we can get to know if a reaction is spontaneous or not by easily measurable terms. We can measure delta H of a system, that's the heat of reaction. We can also measure delta S of the system, and we know we can measure temperature. So this gives us a way to calculate the spontaneity of a reaction or a process with easily measurable variables. Now, if you remember using the entropy term for spontaneity, that the entropy of the universe has to be greater than 0, it's really hard to measure the entropy of the universe. But it's easy to measure the enthalpy of a system or the entropy of a system. And this is where Gibbs, he wanted to rearrange this equation for the second law to make it in terms of easily measured values. So he came up with the term delta G as free energy is equal to minus T delta S of the universe. So the Gibbs free energy combines enthalpy and entropy for a system. So we're getting the Gibbs free energy is really a measure of the entropy of the universe, but we have a relationship that's in terms of enthalpy and entropy of the system. And it's a measure of the spontaneity of a process, and as well as the useful energy available from that process. And the equation, this is an important equation to know. Obviously, you'll be given this on an exam, but it's important to know how to use this equation. And that is delta G of a system equals delta H of the system minus T delta S of the system. For a spontaneous process, delta G has to be a negative. Remember, that's because entropy of the universe has to be positive, but you have that negative sign out there. So delta G is the opposite. It has to be negative for spontaneous. It also has to be positive for non-spontaneous. And for a process at equilibrium, delta G is 0. And that is a pretty important concept. We'll talk about that again. So when we talk about delta G and useful work, delta G is the maximum useful work done by a system during a spontaneous process. In practice, the maximum amount of work can never be done. There's always going to be energy losses. Free energy not used for work is lost to the surroundings as heat. If you want to think about a non-spontaneous process, the delta G for a non-spontaneous process is the minimum amount of work that must be done to the system to make that process occur. And again, a reaction that's at equilibrium, the delta G is 0, which means it can no longer do any work. What are some driving forces for spontaneous changes or spontaneous chemical processes? Well, one driving force is the formation of low energy products. And what does that mean? That means the products have lower energy than the reactants. So delta H, the heat of that reaction, is less than 0 because it's products minus reactants. And these are exothermic processes. That's one driving force for a spontaneous chemical process. Another driving force is formation of products that have a greater entropy than the reactants. So you can think of that as a delta S that's greater than 0 for the reaction. And free energy relates both these, enthalpy and entropy, as well as temperature for a process. And the familiar equation that we've seen on the past few slides, again, delta G equals delta H minus T delta S. A very common way to show delta G for reactions or for processes is using these diagrams, these free energy diagrams. On the left-hand side, you see that the reactants are higher energy than the products. So the overall delta G is less than 0. This is a spontaneous process. And much like in enthalpy, a spontaneous process, or a process that has a negative delta H would be called exothermic because it gives off heat. When we're talking about free energy, a process that has negative free energy is called exergonic, and that means it gives off energy. So the reaction is spontaneous. The opposite, if we looked at a situation here on the right side where the reactants are lower energy than the products, delta G is going to be a positive value. And these reactions are called endergonic reactions. They need energy from outside to drive them. Another way you can think about this, another analogy if you want to think about it, is in terms of a bank account. So if your bank account is up here at the beginning of the month and is down here at the end of the month, that would be a spontaneous process. Why? Because you need money to eat, you need money for rent, you're going to naturally lose money. So that's going to happen spontaneously. If you wanted a situation where you had your bank account down here and at the end of the month your bank account was higher amount, what would you have to do? Well, you'd have to do work. You'd have to go to work to make money. So if you wanted to think about free energy in those terms, I think that might help you just give another way to think about free energy. Okay, let's do a couple of questions. For a reaction that is always non-spontaneous, what are the signs of delta H of the system and delta S of the system? So remember, this is always not spontaneous. Let's write our equation for delta G. Delta G equals delta H minus T delta S. So for a spontaneous process, delta G has to be negative. For a non-spontaneous, it would be positive. How do we get a positive delta G? Well, you have to have a positive delta H, or you have to have a negative delta S to get a positive delta G value, and depending on the magnitude of delta H or delta S. But to always have a non-spontaneous process, both delta H has to be positive and delta S has to be negative. So that correct choice for this would be, let's see, delta H has to be positive, delta S has to be negative, that would be D. And we can see here the effects that delta H, delta S, and temperature have on delta G. This is a table from a different book from last year's text, but it's very similar to table 20.1 in your text. I just like this one a little bit better. So if we look at the signs of delta H and delta S, if delta H is negative, delta S is positive, we're always going to have a delta G that's negative. It's always going to be spontaneous. Conversely, if we have delta H positive, delta S negative, its delta G is always going to be positive, and this will never be spontaneous. But when the signs of delta H and delta S are the same, when they're both negative or when they're both positive, these reactions are going to depend on temperature. So in the case when they're both negative, delta G is going to be less than 0 only at low temperatures. Why is that? If you have a negative delta H and a negative delta S, only when the temperature is small, to eliminate this term from delta S being negative, will you have a delta G that is negative. So temperature has to be low in that case. Now when they're both positive, it's going to be the opposite. It's going to be spontaneous at higher temperatures. That is, delta G is going to be less than 0 at high temperatures. Let's look why. Positive delta H, that's endothermic reaction. Positive delta S. So in terms of spontaneity, a positive delta H is not good. Positive delta S is good. But if it's at a lower temperature, that's going to minimize the delta S term, so we need it to be a higher temperature to outweigh the positive delta H and make delta G overall negative value to be spontaneous. So this table is important to remember this table, and you don't necessarily have to memorize it as long as you can use the equation for delta G and come up with these scenarios on a test. So let's look at temperature and spontaneity. If we consider the reaction H2O solid, so ice, going to H2O liquid water, at 273 degrees Kelvin, which is 0 degrees Celsius. Let's think just in our head, let's think what the delta H would be. You're going from solid to a liquid. That process takes energy to accomplish, so it's an endothermic process, so delta H has to be a positive value. Delta S, on the other hand, you're going from a solid to a liquid, for more ordered to less ordered. So that, again, delta S, that entropy, is also going to be positive. So our delta G, we're going to have a positive value for delta H and a positive value for delta S. So the spontaneity of this process will depend on the temperature. So delta G will be negative above a certain temperature when T times delta S is greater than delta H. If we look at this chart that equates energy and temperature, we see that at 273 for ice, this is the phase change. Delta G actually equals 0, and at this case, delta H equals T delta S. Above this temperature, it's going to be spontaneous. Now, why is that? That's because this purple line represents T delta S, and the green line represents delta H. So above 273, T delta S is a higher value than delta H. So H minus T delta S will give a negative value. Therefore, it will be spontaneous. Below this temperature, T delta S is lower than delta H, and you'll have a non-spontaneous process. So in the case where delta H and delta S are both positive, the line for T delta S here will have a positive slope, a positive value for slope. In the other situation where they're both negative, this purple line would be, it would have a negative slope. And that would be only spontaneous at lower temperatures. And remember from last time, a problem we worked in class, the sign of delta G switches at a point that's equal to delta H divided by delta S. So this is an important equation, important concept to remember, this switching point. Okay, let's practice the transition temperature problem. So given the data below, calculate the temperature at which the reaction becomes spontaneous. Take a few minutes, try to work through this problem, and we'll come work it together. Next slide. If we just think in our heads first, what sign of delta H and what sign of delta S do we expect for this reaction? You have 4 moles of gas of the reactants, and they go to 2 moles of gas of the products. So the entropy for that change, we should expect the entropy to be negative. The enthalpy, on the other hand, that's, in this case, it's a little bit trickier to predict. But for an entropy change, we'd expect a negative value. Well, let's work through this. Let's start with enthalpy. So delta H for the reaction is going to equal a sum of the products minus the sum of the reactants. So the standard enthalpy of formation of the products minus the standard enthalpy change of the reactants. What are those? Products, we have 2 moles of NH3, which is minus 46.1. Then we subtract the reactants. The reactants here are easy because they're both 0. So that term goes to 0. And the delta H we get equals minus 92.2 kilojoules per mole. So let me change the color for delta S. Delta S of the reaction, again, it's going to be the sum of the products minus the sum of the reactants. So that's 2 times 192.5 minus the quantity 191.5 plus 3 times 130.6. Again, those are values for the reactants and the products. So the total delta S is negative 198.3 joules per mole Kelvin. And remember, to compare these two, enthalpies in kilojoules, entropies in joules, we have to convert one of them. Let's just convert enthalpy, so that becomes 0.1983 kilojoules per mole Kelvin. Now we want to find the temperature. Remember that temperature is delta H divided by delta S. Now, how can you find that equation if you didn't remember that equation? Just remember delta G equals delta H minus TS, delta S. And also remember that delta G is going to be 0 at that transition point. The transition between a negative number and a positive number is 0. So you set this equal to 0, delta H minus T delta S. If you add T delta S to both sides, you get T delta S equals delta H. And then you divide through by delta S. So the temperature at that transition is equal to delta H divided by delta S. Okay, so there's a way to come up with that equation without being given it on an exam. So we have minus 92.2 kilojoules per mole divided by minus 0.1983 kilojoules per mole Kelvin. The kilojoules per mole cancel. We're left with a number that's in Kelvin, and we get 465 Kelvin. So that is the temperature where this reaction becomes spontaneous. Right. There are actually two ways of calculating delta G, the standard free energy of a reaction. So the first, we can calculate it using this equation that we have been talking about. In this method, we first need to calculate delta H naught of a reaction, and then we need to calculate delta S naught of the reaction, and then use this equation. So there are 3 steps in this method. The second method, we can actually calculate the standard free energy change of a reaction using tables of standard free energy of formation of the components. So a very similar way that you can calculate the standard free energy of a reaction, the standard enthalpy change of a reaction based on the standard enthalpies of formation. And just like we calculate the standard entropy of a reaction using the standard entropies of formation, we can use a table and just do the sum of the free energies of the products minus the sum of the free energies of the reactants. And a standard free energy of formation, it's very similar to a standard enthalpy of formation. It's 1 mole of a compound of its standard elements, and that's the most stable form of an element at the standard state. And for an element in its standard state, the standard free energy change for that element is 0. So very similar to the standard enthalpy change of formation. Let's try a practice. So calculate the free energy change at room temperature at 298 Kelvin for the following reaction. First, by using the delta H and delta S values, and second, try it by using the delta G formation values. But before you start, let's think about this. What signs do you expect for H and S? So this is a reaction of a hydrocarbon, it's a sugar molecule, plus oxygen, going to CO2 and water. That's a combustion reaction. Think about what you know about combustion. It gives off heat. So we'd expect delta H to be negative. Let's look at delta S. We have 1 mole of solid plus 12 moles of gas. And we get out 12 moles of gas and 11 moles of liquid. So it's going from more ordered to less ordered phases. So what we'd expect delta S would be a positive value. Okay, work through this both ways, and we'll come on the next slide and show you the answers. So the first method, let me change color here, use black. The first method would be to use the equation for Gibbs free energy that's based on enthalpy and entropy. And then calculate. So these are standard states. We're doing it at room temperature, which is standard state. So delta F is going to be, again, the sum of the enthalpies of formation of the products minus enthalpies of formation of the reactants. So there are the products. And the reactants. So delta H is going to be minus 5,644.1 kilojoules per mole. Using the same method for delta S, we're going to have 12 times 213.8 plus 11 times 69.9 minus 360.2 minus 12 times 205. Again, that is products minus reactants. So delta S naught is 514.3 joules per mole, or 0.05143 kilojoules per mole. We plug this into the equation for delta G. And what we get is minus 5,797.4 kilojoules per mole. So let's try it the second method. So the second method would just be using the standard free energies of formation for the products and reactants. So we do a sum of the products first. We have 12 times minus 394.4 for CO2. And then we add 11 times minus 237.2 for H2O. We subtract the reactants, minus 1543.8 for the sugar molecule, and minus 12 times 0 for oxygen. And the sum of this equals minus 5,798.2. So you see that both these methods, we have approximately the same number. There's slight differences, but nothing really significant. As far as if we use the correct number of significant figures, these two values would be equal to one another. And you can see that the second method is by far the easier method, right? Because we're only doing this process of products minus reactants once. Whereas in the first method, we have to do that for enthalpy and entropy, and then we have to enter them into the equation for free energy. So if you have a choice on an exam and you're given these values for delta G of formation, I would strongly recommend that you do that method, just because there's much less of a chance of you making a arithmetic mistake. Let's try some conceptual questions. So which of the following plots shows the correct relationship between delta G on the y-axis and temperature on the x-axis for the sublimation of solid iodine to iodine vapor? The first step in this equation is to write the chemical equation. So our process is solid iodine going to iodine gas. So what do you think the delta S for this transition is? You're going from a solid to a gas. So the delta S, the change of entropy, is going to be positive. Delta H. What is the delta H of this transition? It's a phase change. You're going from solid to gas. Does that take energy or does that release energy? Think about solid water. How do you get it into a gas? You have to heat it. It takes energy to go from a solid to a gas. So it's an endothermic process. So both are positive values. Now let's think about our equation for delta G. Delta H minus T delta S. So if both of these values are positive, delta H and delta S, when is this reaction going to be spontaneous? When is delta G going to be negative? Well, delta G is going to be negative when temperature is higher. Why is that? Because T delta S is going to be bigger than delta H at higher temperatures. So we're going to overall get a negative value for delta G. So which plot here shows that relationship? That would be A. So if we plot delta G on the y-axis, temperature on the x-axis, at higher temperatures, delta G is going to be negative. Okay, let's move on to question 5. The normal boiling point for the element rubidium is 688 degrees Celsius. And the following equilibrium is important in rubidium vapor at the temperature. So we have this equilibrium here. 2 rubidium atoms in the gas phase are in equilibrium with a rubidium-2 molecule in the gas phase. So predict the signs of delta H and delta S for this reaction. So what is this process? What's happening in this equilibrium? We have 2 atoms of rubidium going to a rubidium-2 molecule. So that's a bond formation. What is the delta H, the change in enthalpy for a bond formation? If you remember, bond forming is exothermic. It gives off energy. You can think of that in the reverse terms. What do you have to do to break a bond? You have to provide energy. So bonds take energy to break them. That means they release energy when they're formed. They're exothermic. Bond formation is exothermic. If we look at the number of moles of gas, we have 2 on the reactant side and 1 on the product side. So we're losing moles of gas. So delta S has to be negative. So both delta H and delta S for this process are negative. And final question, for which combination of signs will a reaction always be spontaneous? And this should be easy. Remember, delta G equals delta H minus T delta S. So if delta G is going to be negative for a spontaneous process, delta H has to be negative and delta S has to be positive. That combination would be choice D. Now we're going to shift gears a little bit, if I can get the color to change. And we're going to talk about reactions in the human body. So in living systems, breaking down food that generates heat, the free energy change for those processes, the food breakdown, the generation of heat, they're spontaneous. So the free energy change is negative. Delta G is negative. You also have anabolic processes, building of muscles, that sort of thing, the building up processes. For those, the delta G is actually a positive value. Those are non-spontaneous processes. They require energy. So if you look at life as a whole, the process of life increases the entropy of the universe by converting chemical energy into heat. What is life? Let's talk about that. It's important when we're discussing life to actually define what life is. Life is an organismic state, sorry, that's hard to say. It's characterized by a capacity for metabolism, growth, reaction to stimuli, and reproduction. You can always also characterize life as homeostasis. For example, our body temperatures are pretty much constantly at 98 degrees Fahrenheit. And that doesn't change a whole lot, whether we're in a 100-degree heat, we're in a 70-degree room, or we're outside in 40-degree weather. Our body temperature can stay at a fairly constant 98 degrees Fahrenheit. We can think of life as an ordered system, an ordered enclosed system. And how does it keep that order? Well, it takes ordered molecules from the environment and it creates disordered molecules from those ordered molecules, and it uses that change of entropy in the environment to keep its entropy relatively steady. Well, let's talk about the breakdown of glucose. That's a very important step for living systems. So glucose is used by pretty much every living organism for energy. Here's a glucose molecule. It's a six-membered ring, sugar. And glycolysis is the series of reactions that are used to convert glucose into pyruvate. And this is a major path for metabolism. So we have many different steps in glycolysis, and at the end we get 2 pyruvate ions out. Important reactions in glycolysis and in many biological pathways is phosphorylation. And this is the addition of a phosphate group to an organic molecule. So if we look at glucose, we have glucose and a phosphate molecule. We add the phosphate, we get glucose 6-phosphate. And you see here the phosphates added and water. The delta G for this reaction, however, is a positive value, positive 13.8 kilojoules per mole. It's not spontaneous. But this reaction is required in glycolysis. So how does our body get around this? It gets around this by using a molecule called ATP, adenosine triphosphate. ATP is produced as a result from breaking down foods that we eat, and it can be used to drive non-spontaneous cellular reactions. Here's the structure of ATP. You have the adenosine group out here, which is basically a sugar attached to an adenine, which is one of the 4 DNA bases. But the important part of the molecule is the triphosphate, the 3 phosphate groups it has. If we look at the hydrolysis of ATP to ADP, that's adenosine triphosphate to adenosine diphosphate. This reaction is very spontaneous. It has a delta G of minus 30.5 kilojoules per mole. And that's really the importance of these triphosphate, these phosphate groups, is that they are very high energy. And they can be broken from triphosphate into diphosphate, and this causes a release of energy. A large amount of energy is released. Why is that? Well, you notice that there's charges here. The phosphate groups are all negatively charged, but they're close together in the triphosphate arrangement. So breaking one of those bonds, it decreases the charge repulsion, for one. And then if you also remember resonance structures, here's the resonance structure of the phosphate. And there's also, when the one phosphate group's released, it can go into this resonance form, and that also acts to stabilize it. So when you take one of those phosphates off, you're getting a large stabilization of the phosphate by resonance. You're also removing the charge repulsion. That gives a large amount of energy released. And your body can use the reaction ATP to ADP a very negative free energy value, it can use that reaction to drive non-spontaneous reactions by coupling the two reactions. So a phosphate group from ATP is used in the phosphorylation of the glucose. So we have ATP and glucose, and we get out ADP and glucose 6-phosphate. And we add the two delta G values together. The overall delta G value we get is negative 16.7. So this coupled process then becomes spontaneous. The glucose to glucose 6-phosphate, that reaction is not spontaneous, but when we couple it to ATP to ADP, the removal of the phosphate group, we get a net spontaneous process. And that's really the secret to how life manages to do these non-spontaneous reactions. And these reactions are carried out by enzymes. If you remember, we talked about these free energy diagrams at the beginning of this lecture, and you notice that in this we have an exergonic reaction, that is a spontaneous reaction. Delta G is going to be less than 0 because the free energy of the reactants is higher than the free energy of the products. So this is a spontaneous reaction. But if you notice the green trace represents an uncatalyzed reaction. You have a very high hump here in the middle. Well, what is that? That's the energy you need to put in before the reaction takes place. So even though this is a spontaneous reaction, there's actually quite a large barrier to get between reactants and products. So if you think about in terms of the Jenga demonstration we did in class, the Jenga falling off the table was a spontaneous process, but it required a little push. So how big of a push you need to give a process is this, the height of this hump, the activation energy. What an enzyme does in your body, it lowers that activation energy. It doesn't do anything with the energies of the reactants or the products. All it does is lower the activation energy. And what does this do? It makes it easier to get over that hill. Now let's look at a real-world example of enzymes. And we talked about the first step of glycolysis. Let's use the second step of glycolysis as an example. So the second step, we have glucose 6-phosphate going to fructose 6-phosphate. And this reaction has a negative delta G, so it is spontaneous. If we look at the uncatalyzed reaction, we see that it has a very large activation energy because the transition state is very, very high energy. But when we catalyze this reaction with phosphoglucose isomerase, that's the enzyme that catalyzes the second step of glycolysis, we see that it lowers that transition state. It lowers the activation energy. And how does it do that? It stabilizes the transition state. Now sorry, that's hard to see, but what an enzyme does when it lowers an activation energy, it doesn't do anything with the energy values of substrates or products. It just speeds up the reaction. So this is really a kinetic issue, and we won't be talking about it specifically in this class, but it's important to know if you go on to biochemistry or in analysis of equilibrium systems. This is really dealing with the kinetics of the reaction. It makes the reaction go faster. This is a picture from your book. I think this is a really good picture tying in how your body uses ATP. We use food and oxygen, so food, typically very structured, very ordered molecules. We break those down into CO2 and water. And these reactions, these breakdown reactions, release free energy. And that free energy isn't used directly in your body, but that free energy is used to convert ADP into ATP. So ADP is lower energy, ATP is higher energy. Then your body uses the high energy ATP, converting it back to ADP, and that free energy that reaction releases is then used to synthesize complex molecules from simpler molecules. So it's really a game of taking complex molecules, turning them into simple molecules, and then using that free energy to do the opposite, take simple molecules, turn them into more complex molecules. But I think it's a really good example of how thermodynamics can be used in biological systems and how it is used. And if we talk about life, you have to talk about the cell. That's the compartment of life. That's where life actually happens. And if you remember, I talked about this a little bit before in this class. Cells are made out of molecules that look like this. There's a polar head group and a hydrophobic tail. And when these molecules get together, they can create a bilayer, and that is the outside of a cell, a lipid. The lipid bilayer is the thing that holds the cell together. And inside you have your life, the processes that go into making life happen, and outside you have the environment, where entropy is always increasing, and everything's sort of at a state of higher entropy. Now, if we look at this process from going to single lipid molecules to a bilayer, what would the delta H be for this transition? Well, there's no real phase change. There's no chemical reaction. So the enthalpy of this transition would be approximately 0. The entropy associated with this change from going to single lipids to an ordered bilayer, that's going to be negative, right, with the system when you're looking at the lipid molecules. If they're singular out by themselves, that's a higher entropy state than when they're stacked together and ordered. So delta H is approximately 0. Delta S is negative. That really brings up the question, how is life possible? If delta G equals delta H minus T delta S, delta H is about 0, delta S is a negative number, that means delta G is going to be a positive value, and that's non-spontaneous. So how is life possible? Now, we're going to talk about some intermolecular forces now, switch gears a little bit, but we're going to answer that previous question of how is life possible using a very weak intermolecular force. So intermolecular forces are forces that attract different separate molecules, and they really affect the properties of substances. So if we look at the different types of intermolecular forces, and this is with the higher energy, the higher energy forces at the top of this list, the lower energy forces at the bottom. First we have ion-ion interactions, and those are very strong. They're similar to ionic bonds. Then the next strongest would be an ion-dipole interaction. That's where an ion is interacting with a polar molecule. Next strongest would be a dipole-dipole interaction. That's where you have two polar molecules interacting. And a very important class of dipole-dipole interaction is a hydrogen bond. Next, you have dipole-induced dipole interactions. That's where a polar molecule actually makes a non-polar molecule sort of polarized. It's very, very hard to think about. And then an even weaker force still is dispersion interactions. And those you have induced dipole interactions. And we're going to talk about an important case of dispersion interactions, and that's the hydrophobic force. So these last three, dipole-dipole, dipole-induced dipole, and dispersion interactions, these are collectively known as van der Waals forces, which you might see in some texts or in some contexts. So ion-ion interactions, if you remember, these are governed by Coulomb's law. They're similar to ionic bonds, and the energy of the interaction is equal to the product of the two charges involved divided by the distance between the charges. So as the distance gets closer, it gets stronger. If the charges are increased, it gets stronger. Now if we look at ion dipole, this is the interaction between an ion and the partial charge of a molecule with a permanent dipole, a polar molecule. And we've talked about this before in class too, if you remember, when we talk about an ionic solid dissolving in water. The water has a permanent dipole, it's a polar molecule, and you see that it can align itself so the dipole interacts with the particular ion, the plus ion or the minus ion. And what you get from this is known as a sphere of hydration. So water molecules, these polar molecules, can form very ordered cages around ions. The next interaction is a dipole-dipole interaction. So these are attractive forces between two polar molecules. And the most important type of dipole-dipole interaction is a hydrogen bond. These are the strongest dipole-dipole interactions. What this requires is that the hydrogen atom is covalently bonded to a strongly electronegative atom, such as fluorine, oxygen, or nitrogen. And when that happens, you get a dipole on that bond. So here we have a water molecule. There's a dipole on one of these bonds between the oxygen and the hydrogen. And you notice that on this other oxygen atom, there's a dipole as well. So the negative dipole of one water molecule can interact with the positive dipole of another water molecule, and that creates what's known as a hydrogen bond. And you see that you have that same case for NH3 and HF. Hydrogen bonds are very important in biology, and one of the main main examples of a hydrogen bond in biology is that of DNA. The reason there are complementary bases and that they come together and form the double helix is that the complementary bases actually hydrogen bond with one another. And this is important because it keeps the genetic information stable until it's ready to be replicated or read. And you have certain enzymes that can come through and break those hydrogen bonds when they're replicating the DNA. But when the DNA is sitting there dormant, it's a very stable structure. And so the molecule doesn't get damaged. So here we see the interactions between the G and the C base pairs. There's 3 hydrogen bonds, and the A and the T base pairs only have 2 hydrogen bonds. Hydrogen bonding is also important in enzyme chemistry, and you don't really need to know any of these specifics, but we talked earlier in the lecture that an enzyme stabilizes the transition state. So if we look at this diagram here, step 1, that's the enzyme without any substrate in it. Step 2, the substrate enters the enzyme active site. Step 3 is a transition state, but you see that these dashed lines, those represent hydrogen bonds. So they're hydrogen bonding with the transition state, stabilizing it. And then step 4, we have the reaction occurring. And then the final step, going from 4 to 1, we release the product. So hydrogen bonding, very important in enzyme chemistry. And a typical hydrogen bond, they're on the order of 2 to 3.5 angstroms. And they are a weak force, but they're typically about 20 kilojoules per mole. There's a really wide range of strengths of hydrogen bonds, but typically a typical number would be 20 kilojoules per mole, and that's actually quite high. So they're very very important. 20 kilojoules per mole is if you're thinking about in terms of lowering an activation energy, that can be quite large. So the final class of intermolecular forces we're going to talk about are dispersion forces. Sometimes they're also called London forces, and these are caused by temporary dipoles, or also another term for that is induced dipole. And what an induced dipole is a separation of charge in an atom or a molecule due to a momentary uneven distribution of electrons. So you can have a molecule that's normally nonpolar become polar temporarily. So if we look at a system where we have 2 nonpolar molecules and they come together, there can be an interaction where their electron clouds shift and create a momentary dipole. And this shift in one molecule, momentary dipole, can cause a shift in another molecule's momentary dipole. And they can align where the negative sign of one dipole is pointed towards the positive side of the other dipole, and there can be a positive interaction there. You can also get this You can also have this sort of induced dipole, it's more commonly seen when you have a one polar molecule interacting with a non-polar. So a water molecule interacting with an oxygen molecule. This dipole from the water can actually influence the electron cloud of the O2 and create a temporary dipole on the oxygen. And that creates an attractive force. Right. The important thing to note about intermolecular forces is that the physical properties of substances are influenced heavily by these intermolecular forces. And what are some of those physical properties? One is the melting and boiling points of substances. As more intermolecular forces exist in a substance, or as they're stronger intermolecular forces, that acts to increase the melting point and the boiling points of those substances. So the stronger the intermolecular forces of a substance, the higher the melting point and the higher the boiling point. Another factor that's influenced is solubility. So in polar solvents, the solubility increases as polarity of a substance increase. The same can be true in a nonpolar solvent. The solubility increases as the polarity decreases. And finally, the solid state structure can be influenced by these. And an example of that is in water. It actually expands as it freezes, and that is due to hydrogen bond formation. So hydrogen bonds are harder to form in the liquid phase, but they form more fully in the solid phase. There's more hydrogen bonds in solid liquid than there are in liquid water. An important diagram to really know how to read is a phase diagram. And this becomes important in phase transitions and being able to tell what the physical state of a substance is given its temperature and pressure. So what a phase diagram is a graphical representation of the stabilities of physical states of a substance as a function of temperature and pressure. And the lines on the phase diagram are called equilibrium lines, and they represent the changes between solid and liquid, liquid and gas, and solid and gas under specific temperatures and pressures. Let's try to practice a phase diagram type of a problem. So we see a phase diagram here where we have pressure on the y-axis, temperature on the x-axis, and this is a phase diagram for water. Sorry, this is a phase diagram for CO2, not water. So what happens when the temperature of CO2 is increased from minus 100 degrees Celsius to 200 degrees Celsius at a pressure of 25 atmospheres? So this is negative 78. So negative 100 will be probably about there somewhere, let's say. This is 1 atmosphere, so this is 73, so 25 should be around there. So at 25 atmospheres and minus 100 degrees Celsius, this is what point we'd be at. So we'd be a solid. It'd be solid CO2. Now it says we increase the temperature to 200 degrees at a constant pressure, so pressure stays at 25. So as we do that, you see we hit this blue line, and that is a phase transition. So at that line, we're going from solid to a liquid. And as we cross that line, we're now in the liquid phase. Keep going, we hit the red line. That's the phase transition between liquid and gas. So there's a second phase transition. And then we continue on until up here somewhere where it would be 200 degrees Celsius. These are simple enough to read on their own, but when you see them the most is with a question, if they're asking what would the enthalpy change from going to this dot be, well then you know if you follow that line you hit 1, 2, you get 2 phase transitions, so that enthalpy change would be delta H of going from solid to liquid, which is melting, plus delta H going from liquid to gas, which would be boiling or vaporization. Also, you can ask the heat, how much heat is required to go from minus 100 degrees to 200 degrees. How would you answer that? Well, you know that portion, the heat would be NCP delta T. That would be N, heat would be N times delta H of that phase transition. This portion would be heat equals NCP delta T. We have another phase transition, so heat would be Q equals N delta H. And finally, final heat would be heat times NCP of the gas phase, delta T. You would add those heats together to find the total heat required to go from negative 100 to 200 degrees at a constant pressure. So the second physical characteristic that's really influenced heavily by intermolecular forces is solubility. And solubility depends on the relative strength of solute-solvent interactions compared to solute-solute or solvent-solvent interactions. And one important rule to remember with solubility is that like dissolves like. What that means is ionic or polar solutes are going to be soluble in polar solvents. Nonpolar solutes will be soluble in nonpolar solvents. So here's an example of a polar solute being soluble in a polar solvent. If we look at methanol, it's polar molecule. Water, another polar molecule. They both can form hydrogen bonds with other similar molecules. And when they're mixed, that holds true. They can form hydrogen bonds with one another. And they form a solution. Now if we look at an example of two things that are not similar, that would be water and octane. Water's polar, octane now is nonpolar, and they can't form any interactions with one another. And they do not mix. There's no solution that's formed. When we talk about solubility, it's not just liquids. We can also talk about gases, solubility of gases. And that's where Henry's law comes into play. And Henry's law basically states that the solubility of a gas is proportional to the partial pressure of that gas. And the equation would be C of the gas, so the concentration of the gas in a liquid, is equal to K sub H, which is Henry's law constant. And these values are different. It depends on what gas you're looking at. And That's multiplied by P of the gas, so the pressure of the gas above the liquid. So why is this important? Well, in our bodies, we need oxygen, but our veins aren't filled with gas, they're filled with a liquid, with blood. So for us to live, we really need to breathe in gaseous oxygen and have that dissolve into our liquid phase, our blood, to be transferred to our whole body. Another example of where it becomes important is CO2. When we release more CO2 in the atmosphere, not only is it a greenhouse gas and can lead to higher temperatures, but the higher partial pressure of CO2 in the atmosphere means that more CO2 is dissolved in the oceans, so the concentration of CO2 in the oceans becomes higher, and this causes an increase of the pH of oceans or lakes, and that can harm aquatic life. So this two examples of where Henry's law comes into play with the solubility of gases in water in particular. So when we look at solubility behavior, there's a couple terms we can use. One is hydrophobic. This means water fearing, and this interaction repels water, diminishes water solubility. The other term is hydrophilic. This means water loving. This interaction attracts water, promotes water solubility. So hydrophobic, that term usually means nonpolar molecules are hydrophobic. Hydrophilic would be polar molecules. So if we look at two nonpolar molecules, they can stack on top of one another and form a dispersion force. They're both nonpolar. They have a induced dipole interaction between the two. And this dispersion force also, if we look at water molecules, if these were in water, the water molecules would be excluded from these hydrophobic molecules. And you can also see here the ends of these molecules, these OH groups, those are actually polar, right? Because that carbon-oxygen bond's a polar bond, so that's a hydrophilic part. So the water molecules would be very ordered around that particular part of the molecule. And this is where the hydrophobic force comes from. If we look at an example of a protein, so here we have a protein that's unfolded. And here we have a folded protein. The function of a protein depends on its structure, depends on its three-dimensional shape. It depends on how it's folded. So this step from going from unfolded string of amino acids to a folded protein, if we look at the thermodynamics of that step, you have hydrophobic amino acids. Those are shown in black, and they tend to associate in the center of a protein. And this is actually the major driving force in protein folding. Now, when we look at the hydrodynamics, the thermodynamics of this step, what would the entropy change be if we go from unfolded to folded? You're going from more degrees of freedom in that unfolded linear chain to less degrees of freedom in the the folded protein. It's more ordered. So entropy would then be a minus delta S for this transition. It's going to be less than 0. So the term negative T delta S would be positive. And as far as spontaneity goes, that's not a good thing. Now if we look at the internal interactions, and those are, so we have an entropic loss because of graded order. If we look at the internal interactions that are going on when the protein folds, primarily due to electrostatic interactions, so charged amino acid groups that are close to one another can have electrostatic ion-ion interactions. So this makes bond formation, if you want to think about ionic bond formation, which is an exothermic process. So delta H is also going to be negative, but not negative enough to offset this entropic change. So what happens? Why is protein folding spontaneous? Well, there's also another effect, and that's the hydrophobic effect. And the hydrophobic effect makes it so that protein folding is an overall negative delta G and a spontaneous process. So we come back to this question of how is life possible? We've seen the hydrophobic effect helps proteins fold. Well, it also makes cell formation, the cell membrane formation, possible. And if you remember going from single lipid to lipid bilayer, the delta H of that is about 0, no phase change, no chemical reaction. The delta S is negative. You're going from less order, more degrees of freedom, to more ordered, less degrees of freedom. So what's happening here? Why does this happen? Well, the delta S of the system is negative, but the delta S of the surroundings is very, very positive, much, much greater than 0. Why? Well, when you have a single lipid in solution, the water molecules can't interact with this hydrophobic tail. So they're forced to interact with themselves. And you get what's known as a solvent cage. So there's a very ordered cage of water molecules around this tail, this hydrophobic tail. What that does, that is actually a very low entropy state for the water molecules because they're so ordered around that hydrophobic tail. What happens when the lipids form a bilayer, those hydrophobic tails interact, those water molecules are released into solution. So they become free water molecules. So the increase of entropy of the surroundings, basically of the water molecules, is very, very positive. And this acts to drive cell formation, protein folding. So this hydrophobic force is due to the increased entropy of the water molecules. And this really is how life is possible. This very weak force, this dispersion force, the hydrophobic force is what makes life as we know it possible. And that's it's very hard to think about that such a weak force can be responsible for life. All right. So what I think is really important for the exam that you know is the relative strengths of the intermolecular forces. So if we go back and do a summary here, this figure's from your book. It's not showing the ion-ion interactions. So if you had a plus-minus interaction, basically an ionic bond, that's the strongest. That's followed by ion dipole, where you have one ion, one polar molecule. Next strongest would be hydrogen bonds. If you remember, hydrogen bond is a type of dipole-dipole interaction, but the hydrogen bond is the strongest. Then that's followed by an ion-induced dipole, so an ion interacting with a nonpolar molecule and creating a temporary dipole. And then that's followed by dipole-induced dipole, and followed by dispersion or London forces. And if you remember, the hydrophobic force is the most important example, really, of dispersion forces. It's the weakest intermolecular force, but it's also what's responsible for cell formation, for protein folding, for processes that are very important for life.